I want you to picture, just for a second, what a data center actually looks like.
Oh, like the really massive industrial scale ones.
Yeah, exactly. Because if you're trying to run the kind of massive artificial intelligence models we hear about every single day, you're usually relying on this huge industrial scale of computing.
Right, right. We're talking rows and rows of giant refrigerator-sized server racks.
Uh-huh. With the deafening cooling fans and power cables that are literally thick enough to moor a ship.
Yeah, it's a massive physical footprint.
Totally. But then I want you to look down at the desk in front of you, or your lap. Just look at a thin, completely silent, modern consumer laptop.
It's quite a contrast.
It really is.
Yeah.
And today we are looking at this genuine technological mystery. Like, how did a consumer laptop evolve into a machine that is capable of running data center level artificial intelligence right there on your desk?
And doing it completely offline, too.
Exactly. Offline and without literally melting through your table.
It's a fascinating structural reality, honestly, because we are sitting with hardware capabilities today that just completely defy all the traditional expectations of desktop computing.
Right.
And, the really wild part is that the way we got here wasn't even an intentional AI strategy to begin with.
Yeah, that's the craziest part to me. So to figure out how this actually happened, we are taking a deep dive into an April 2026 Substack article.
Oh, the one from SpiralSeekr.
That's the one. It's titled Apple M-Series Silicon, Architectural Innovation, Historical Necessity, and 2026 LLM Inference Efficacy.
Quite a mouthful of a title.
It is, yeah. But our mission for this deep dive is to basically decode a very specific and honestly a surprisingly dramatic piece of tech history.
Right, because we're going to explore how Apple's highly publicized breakup with Intel years ago accidentally built the ultimate hardware architecture for running massive local large language models today.
Exactly. And we should probably set the stakes for you as a listener right away.
Gotcha.
Because, this isn't just some boring comparison of computer specs,
No, not at all. It's not just a list of benchmark numbers. We are looking at a fundamental shift in who actually gets to hold and control massive computational intelligence.
Right.
Because the barrier to high-level, entirely private AI has essentially been shattered for everyday users.
Yeah.
And the root cause of that goes back like a half decade.
Yeah, to really understand these 2026 AI powerhouses, we have to rewind to why Apple radically changed their computer chips in the first place.
Right, because as you said, they absolutely didn't do it with AI in mind.
No, they did it out of sheer frustration.
Yeah, they really did. If we look back to the formal announcement in June 2020, Apple was publicly departing from Intel.
Which was huge news at the time.
Oh, massive, because for over a decade, Apple had relied incredibly heavily on Intel's x86-64 processors for literally their entire Mac lineup.
Right.
But there's this massive physical conflict brewing between Apple's hardware design philosophy and, well, Intel's physical realities.
Because Intel's architecture required a really high power draw to reach its peak performance levels, right?
Exactly. And with high power draw comes an immense amount of heat.
And, Apple is notoriously obsessed with creating those razor-thin laptop designs.
Right. They want everything sleek and light. But the thermal dissipation capacities of those ultra-thin chassis designs, they simply could not handle the heat generated by the Intel chips.
So what happens when they get too hot?
Well, when a processor gets too hot, the system engages in what's called aggressive thermal throttling. It artificially slows itself down to avoid literal melting or, permanently damaging the hardware.
Oh, wow. So you had these professionals buying really expensive top-tier machines
that literally couldn't sustain their peak compute power for more than a few minutes without severely downclocking.
That sounds incredibly frustrating.
It was a total dead end for Apple's product roadmap. They couldn't push the performance any further in the form factors they wanted.
And SpiralSeekr actually points out some incredible insider detail about the friction behind the scenes, too. Because it wasn't just about heat.
No, it was also about stability.
Right. The source highlights a quote from a former Intel principal engineer, Francois P. Noel. And he noted there were, abnormal quality assurance issues and actual underlying architecture bugs in Intel's Skylake processors at the time.
Yeah, and Apple, mainly because of how closely they monitor their own operating system, was apparently the highest reporter of these bugs.
Which is wild. When your own software engineers are constantly having to write workarounds for someone else's hardware flaws.
Yeah, that kind of stagnation really accelerates the decision to just pack up and leave.
So to solve both the heat issue and the reliance on this external vendor, Apple didn't just switch to another chip maker.
Right. They decided to build their own silicon. They shifted to an ARM64-based system on a chip, or SoC.
And moving to an ARM-based architecture gave them, what, a much better performance per watt ratio?
Significantly higher, yeah.
Yeah.
They finally achieved the processing power they actually wanted without the extreme heat. It allowed for sustained, heavy compute in a really thin laptop.
That makes sense.
But crucially, this move to vertical integration, where they designed the hardware die to perfectly match their Mac OS software, that allowed them to put custom hardware accelerators, like the neural engine, directly onto the processor itself.
Okay, let's unpack this system on a chip design for a second, because it is literally the absolute crux of everything that happens with AI later on.
It really is the foundation.
So think of a traditional PC setup as this massive, super busy restaurant kitchen. You have the central processing unit, the CPU, acting as your master chefs.
Okay, I like this.
Right. Then you have the graphics processing unit, the GPU, acting as your decorators and your pleating specialists.
Makes sense.
But in a traditional PC, the chefs are in one room with their own dedicated pantry, which is the system RAM. And the decorators are in a totally different room with their own separate pantry called the VRAM.
Right, the video RAM.
Yeah. So whenever they need to work on the same complex dish, they are constantly wasting time physically carrying ingredients back and forth across this long hallway.
And in computer terms, that hallway is the PCIe bus.
Exactly. And it's just an incredibly inefficient way to share data, right?
It really is. So when Apple moved to their own silicon, they introduced what they call the Unified Memory Architecture, or UMA.
Right, the UMA.
Yeah, and to use your kitchen analogy, they basically knocked down the walls between those rooms. Now, the CPU master chefs, the GPU decorators, and, the specialty neural engine prep cooks are all standing around one giant shared prep table.
Oh, wow. So they're all in the same space.
Exactly. That single table is the unified memory pool.
Right.
They can all read and write the exact same data at the exact same time without copying anything or carrying it down any hallway.
And what's wild to me is that this giant shared table was originally designed just to make the laptops run smoother, right? And to use less battery.
Purely for efficiency and thermals, yeah.
But entirely by accident, knocking down those kitchen walls created the exact structural advantage required to run massive large language models in 2026.
It's the ultimate happy accident. Because if you've ever tried to run a massive language model on a standard desktop PC, you know exactly what happens. You slam right into the VRAM wall.
Exactly. Consumer discrete GPUs, the traditional graphics cards you slot into a PC motherboard, they have very strict physical limitations on their VRAM.
Like, how limited are we talking?
Well, even today, mid-tier hardware usually caps out at about 8 gigabytes of VRAM. High-end consumer hardware might hit maybe 24 gigabytes.
Right. But local LLMs, especially the kind with billions of parameters, they're massive. Like, a 24-gigabyte pantry isn't nearly big enough for them.
Not even close. So when an AI model's data requirements exceed that GPU's VRAM ceiling, the system has no choice but to start offloading that excess data.
It has to carry down the hallway.
Exactly. Over that PCIe 5.0 bus, back to the regular system RAM. And the moment that happens, your data bandwidth just plummets.
Oh, really? How bad is the drop?
You drop from the blazing fast internal speeds of the graphics card down to roughly 64 gigabytes per second over the bus.
Oh, wow, that's a huge bottleneck.
It is. The entire system basically chokes, and token generation, which is the AI actually spitting out its answer to you, it just stalls out entirely. Right, but Apple doesn't have a small VRAM pantry anymore. They just have the huge unified table.
Exactly. What's fascinating here is that Apple's M4 and M5 series chips scale that unified memory architecture up to staggering sizes.
How big are we talking now?
We're looking at configurations with 64 to 128 gigabytes of ultra-fast LPDDR5X memory. On an M4 Max with 128 gigs of unified memory, the system dynamically allows you to allocate over 100 gigabytes of that strictly to the GPU.
Wait, hold on. I'm actually stuck on something pretty basic here.
Sure, what's up?
We spent like 40 years of computing history obsessed with processor speeds, right? Megahertz, gigahertz, how fast the chip does actual math.
Right, the raw compute cycles.
Yeah. So why are we suddenly pretending memory capacity is the only thing that matters for AI? Shouldn't a smarter, faster processor core be the ultimate gatekeeper here?
That's a really common question, but the thing is, the processor cores are just executing the math. But the math is entirely bottlenecked by data delivery.
Okay, explain that a bit more.
To run a local LLM, the hardware has to physically hold two vital components in its active memory at all times. First, you have the model weights.
Which are the billions of parameters, right? Like the AI's actual knowledge base.
Exactly. And second, you have the key value cache, or KV cache, which acts as the AI's short-term memory of your current conversation with it.
Got it. So it needs both instantly.
Yes. Holding those two massive data sets in memory and being able to access them instantaneously, that is the true gatekeeper of AI inference.
So if it can't reach them fast enough.
If you have the fastest processor core in the world, but it has to wait for data to travel across a slow PCIe hallway, that core is just sitting there idle. It's doing nothing. Memory capacity and the speed at which you can read it is basically the fuel line for the entire operation.
Okay, that makes total sense. And you mentioned holding the model weights earlier. The source actually brings up running quantized versions of models, like llama.cpp or Qwen.
Yes, quantization is huge for local execution.
And when we say quantized, we're basically talking about compression, right? Like turning a massive raw photograph into a smaller JPEG.
That's a perfect analogy, yeah.
So you lose a tiny fraction of mathematical precision, but it dramatically shrinks the physical size of the model so it can actually fit into that 100-gigabyte memory pool.
Right. That compression is vital. And when you combine it with the unified memory, it permits the loading of heavily parameterized models entirely into a laptop's high bandwidth space.
Completely bypassing that PCIe hallway bottleneck.
Exactly. Bypassing it entirely.
Okay, so the unified memory solves the capacity problem. We can physically squeeze a 70 billion parameter intelligence onto a laptop.
We can fit it, yes.
But we need a reality check on the actual speed here, because just having a big enough prep table doesn't mean you're actually serving food at data center speeds, right?
That is the crucial distinction, yes. And the source provides some pretty sobering benchmarking data from an archive paper published in February 2026.
Okay, let's hear the numbers.
If we look at an M4 Pro chip running a quantized Gemma 312B model, it processes at approximately 260 tokens per second.
I mean, 260 tokens per second is incredibly fast for reading. That looks practically instantaneous to a human user.
It absolutely looks fast on a screen. But true data center hardware scales very differently. A dedicated server farm processes upwards of 10,000 tokens per second.
Oh, wow. Okay, yeah, that is a completely different league.
The M series is operating at a fundamentally different scale.
And I imagine that scale becomes a massive issue when we move away from just, like, chatting with a single AI in a single window, right? Like when we start talking about multi-agent workflows.
Well, exactly. Multi-agent workflows are where you hit the wall.
Because imagine you're developing an app. You have one local AI agent writing the Python script, another agent acting as a security auditor reviewing that script in real time, and a third generating the user manual based on their output.
All running simultaneously on the same chip.
Yeah, that sounds like a heavy lift.
It places an immense strain on that KV cache, the short-term memory we discussed earlier. The benchmark data shows that an M4 Pro, which has roughly a 10.2 gigabyte cache budget, it can only handle 3 concurrent LLM agents maintaining an 8K context window simultaneously.
Wait, really? Only 3?
Only 3. After that, it has to start evicting and reloading.
Here's where it gets really interesting if we try to visualize how that KV cache actually works under strain. Think of the AI like a brilliant detective.
Okay.
The unified memory pool is this sprawling archive of case files, right? The model weights containing all the knowledge in the world. And the detective can access any file instantly.
Right.
But the detective's actual physical notepad, the KV cache, is tiny.
It's very limited, yeah. And when the detective is interviewing suspects, they can easily keep track of the alibis for 3 suspects on that little notepad.
Exactly. But the moment you ask them to track a 4th suspect at the exact same time, they just run out of paper.
They literally have to start erasing their notes about suspect number 1 just to write down what suspect number 5 is saying.
Yes. And if they need to ask suspect 1 a follow-up question later, they have to go all the way back to the main archive and reconstruct their notes from scratch.
Which is an incredibly expensive operation in terms of computational time. The system is forced to constantly evict old caches and reload new ones from scratch.
So that constant churning just slows everything down.
It slows token generation to an absolute crawl. So, while the M4 architecture provides a massive structural advantage by eliminating the PCIe memory bottleneck, it is still bound by its total memory capacity and bandwidth when scaling to heavy multi-agent workloads.
So if I'm trying to run a team of these AI agents and my M4 chip taps out at 3 before it starts aggressively dumping its own memory, I mean, that sounds like a hard physical wall.
It really is a hard limit.
Like the kitchen table analogy breaks down completely if the chefs have to start throwing ingredients away just to make room to work.
Exactly. And that physical limitation forced Apple's engineers to rethink the actual silicon layout for the next generation. Which brings us to the March 2026 release of the M5 Max.
Okay, the M5 Max, what did they change?
The primary architectural revision here is what Apple designates as Fusion architecture.
Okay, but rather than just listing specs, what does Fusion actually mean under the hood? Like, how did they physically build this to handle that memory eviction problem?
Well, they essentially bridged two third-generation 3-nanometer dies. They took two completely separate processor brains and stitched them together with an ultra-high bandwidth interconnect.
Oh, wow. So they just glued two chips together.
More or less. They're making two separate chips believe they are a single unified brain, and doing this physically doubles their data pipes and core counts without having to redesign the core architecture from scratch.
So you just end up with massive numbers across the board.
You do. The maximum M5 Max configuration scales up to an 18-core CPU. That's broken down into 6 high-performance supercores and 12 multi-thread optimized performance cores.
That's a lot of chef.
It is. And alongside that is a massive 40-core GPU. But crucially, they integrated dedicated neural accelerators into literally each individual GPU core.
Wait, in each core?
Every single one. And all of this is fed by that unified memory, which on the M5 Max hits a peak bandwidth of 614 gigabytes per second.
614 gigabytes per second. I mean, that is just a fire hose of data.
It's massive.
And SpiralSeekr provides specific benchmarks to show what that fire hose actually translates to for you at home, right?
They do, yeah. If you run a smaller model like a quantized DeepSeek R1, which has 8 billion parameters and takes up about 6.3 gigs of space, the M5 Max churns out roughly 73 tokens per second.
Okay, that's pretty fast.
But what happens when you throw an absolute behemoth at it? Say, the Qwen 2.5, which is a 72 billion parameter model with a 60 gigabyte footprint.
That's huge. How does it handle that?
Even with that massive payload, the M5 Max processes it at roughly 7.6 tokens per second.
Oh, okay.
The benchmark data shows that token generation speed on the M5 Max correlates directly with the memory bandwidth divided by the model size. It consistently operates at about 73% to 75% efficiency of its theoretical maximum bandwidth.
Now, I feel like 7.6 tokens per second might sound to some people like a massive drop from 260, but let's contextualize that for a second.
Yeah, let's break it down.
7.6 tokens translates to the AI typing out about 5 or 6 words a second. That is literally faster than most humans can read, let alone type.
Exactly.
And you are running a 72 billion parameter supercomputer level brain on a machine that's just resting on your knees without it crashing.
It's phenomenal.
Yeah.
And the architectural leap also profoundly impacts prompt processing, or, the time to first token.
Oh, right. Like when you give the AI a huge block of text to read before it answers.
Exactly, like asking it to summarize a massive PDF. That initial reading phase requires moving an immense amount of data instantly. And Apple reports a 6.7x speedup in this prompt processing phase relative to the older M1 Max architecture.
6.7 times faster. That's incredible.
It really is.
Yeah.
And this is directly attributed to that wider fused data pipe connecting the 16-corner engine to the unified memory pool.
I do want to challenge this narrative just a little bit, though.
Sure, go for it.
Because we're talking almost exclusively about raw silicon here, right? Fused dies, wider pipes, nanometer fabrication. Are we just brute forcing this problem with hardware? Or does the actual software backend you use make a difference? Like, can bad code strangle good silicon?
Oh, absolutely. Hardware utilization is entirely dependent on the software frameworks instructing it. The source highlights a massive disparity in optimization, actually.
Oh, really? Like what?
So if you run a quantized 16 gigabyte model using a generalized software backend, like llama.cpp, you get a certain baseline speed.
Right. Because llama.cpp is pretty common.
It is, and it's incredibly versatile. But it's a generalist. It has to translate its instructions to work on almost any machine out there.
But what if you use Apple's native software?
Well, if you run that exact same workload using Apple's native MLX framework, you see nearly a 1.9x speedup.
Almost double the speed just from software?
Yes, because MLX is code written specifically to speak the exact physical language of Apple's silicon. It directly addresses the unified memory and the neural accelerators without needing those extra translation layers.
Oh, wow.
Yeah, just by using hardware-optimized software, the exact same machine hits over 31 tokens per second on that 16 gigabyte model. The framework matters immensely.
So, what does this all mean when we finally pull all these threads together? We've looked at Intel's heat throttling causing a corporate breakup.
Right.
We've looked at broken kitchen walls creating a unified memory prep table, those tiny detective notepads forcing memory eviction, and the engineering marvel of fusing 3-nanometer chips. What is the ultimate takeaway from this whole landscape?
The ultimate takeaway here is basically a story of scale and democratization. I mean, is a 614 gigabyte per second M5 Max chip as fast as a 3.35 terabyte per second NVIDIA H100 data center chip?
No, obviously not.
Right. No, it is still an order of magnitude slower.
Yeah.
But comparing the two misses the point entirely. The Apple M series architecture fundamentally bypasses the 8 gigabyte VRAM bottleneck that has just strangled standard desktop computing for years.
It's a completely different paradigm.
It is. It allows you to fit data sets that previously required an entire server rack into a consumer device.
And for you listening, whether you are a developer testing out complex multi-agent code, or a professional summarizing dense reports, or honestly just someone who is deeply curious about where this technology is heading, this changes the rules of engagement.
Completely changes them.
Because it means you no longer have to rely solely on an internet connection to the cloud to run complex, world-class AI. You literally have the architectural capacity to run these systems on a battery-powered device.
Which is huge for privacy, too.
Exactly. Your private data, your sensitive documents, and your proprietary code. They never have to leave your machine to be analyzed by some massive neural network somewhere else.
The localized hardware barriers have effectively fallen. And it's entirely because of a design pivot intended to keep laptops from getting too hot, like 5 years ago.
Think back to that image we started with at the beginning. The noisy, incredibly hot, massive data center versus the silent, thin laptop sitting on your desk right now.
Yeah.
The sheer gravity of computing power has migrated downward out of the industrial space and right into the personal space.
It really has.
Which leaves us with one final, lingering question to ponder as we wrap up today's deep dive. If consumer hardware can now locally hold and process the entirety of a 72 billion parameter intelligence completely offline, how will this shift the balance of power away from the massive cloud-based tech giants? And how will it entirely redefine what we consider personal computing and data privacy in the decade to come?
That is the big question.
It really is. Thank you so much for joining us for this deep dive. We'll catch you on the next one.